You ever notice how different languages handle CPU cycles? Like Python versus C#, they're like night and day.
Yeah, Python's definitely heavier on the CPU due to its interpreted nature.
Exactly. And it's not just about the language itself, but also the runtime environment. JVM, for Java, for instance, has some really interesting optimizations that can make a huge difference in profiling.
True, especially with JIT compilation kicking in after a while.
Right, JIT compilation. It's amazing what modern compilers can do under the hood. But, I still find it fascinating how much impact your coding style can have too. Take recursion, for example. Some languages handle it beautifully, others, not so much.
Especially in Python, recursion depth is limited by default settings.
Absolutely. And hitting that limit can lead to stack overflows pretty quickly. Speaking of which, did you know that Go handles concurrency through coroutines? They're lightweight threads managed by the Go runtime, which means less overhead compared to traditional OS-level threads.
That does make Go great for high concurrency applications.
It sure does. But let's talk about memory usage now. Have you noticed how certain data structures can drastically affect both memory and CPU usage? Lists versus linked lists, arrays versus hash tables. It's all about trade-offs. Speaking of trade-offs, let's talk about memory allocation strategies. Have you seen how different platforms handle this?
Yeah, it varies quite a bit. Linux uses glibc, which has its own set of allocators.
Exactly. And Windows has its heap management functions too. Both have their quirks and performance characteristics. Did you know that malloc in glibc uses arenas to manage threads efficiently?
Interesting. I didn't know that detail.
It's crucial for multi-threaded apps. Each thread gets its own arena initially, reducing contention. Now, compare that to Windows Hepalock. It's simpler, but can lead to fragmentation issues if not managed carefully.
Fragmentation can be a real headache in long-running processes.
Absolutely. That's why understanding the underlying mechanisms is key. For instance, on mobile devices like iOS or Android, the allocators are optimized for low power consumption and limited resources. They often use more aggressive techniques to reclaim memory.
Makes sense given the constraints of mobile environments.
Definitely. And don't forget about garbage collection and managed languages like Java or .NET. Those systems have sophisticated GC algorithms designed to balance performance and memory efficiency.
The trade-offs there are significant, especially with concurrent GC or
Oh yeah, concurrent GC can really impact CPU usage during heavy workloads. But it's essential for keeping interactive applications responsive without freezing up. So, what do you think about using custom allocators for specialized tasks? Say, fixed size blocks for small objects.
custom allocators could definitely help optimize specific use cases.
Speaking of optimization, have you ever used any real-time CPU monitoring tools for profiling? They can be incredibly helpful.
Yeah, I've used some basic ones. What do you recommend?
Well, there are a few standouts. On Linux, Perf is fantastic. It gives you detailed insights into CPU usage and even lets you trace system calls and function calls in real time.
Perf sounds powerful.
It really is. And then there's ATOP, which is great for a visual overview of processes and their CPU usage. For Windows, Process Explorer from SYS Internals offers similar capabilities.
Visualizing the load can make it easier to pinpoint bottlenecks.
Absolutely. Gut. And let's not forget about profilers integrated into development environments. For example, Visual Studio has a built-in profiler that works well for our .NET applications. It provides timeline views and call stacks to help identify performance hotspots.
Integrated profilers can be very convenient.
They sure can. Another tool worth mentioning is gprof for CCI programs. While it's more traditional, it still provides valuable data on function execution times and call counts.
Classic tools can still be useful.
Definitely. The key is to choose the right tool based on your needs. Real-time monitoring is crucial for identifying those fleeting spikes in CPU usage that might otherwise go unnoticed. Speaking of which, let's dive into garbage collection and its impact on memory profiling. It's a critical aspect that can really affect application performance.
Absolutely, especially in languages like Java or .NET, or Lindy.
Right. Why? Garbage collection is designed to automatically manage memory, but it can introduce pauses and affect CPU usage. Have you ever profiled an app during GC runs?
A few times, but I always found it tricky to interpret the results.
It can be complex. Different GC algorithms have varying impacts. For instance, the generational GC used in many JVM implementations separates objects into generations, young and old, and collects them differently.
That sounds like it adds another layer of complexity. No, can you? No,
Indeed, young generation collections are usually faster since they focus on short-lived objects, while full GCS targeting the old generation can take much longer and cause noticeable pauses.
those long pauses can be disruptive in real-time applications.
Very true. That's why understanding how GC works is crucial for optimizing memory usage. Tools like Visual Vim for Java or .memory for .memory .NET provide detailed insights into GC behavior and memory usage patterns.
Detailed insights would definitely help pinpoint issues.
Exactly. With these tools, you can see exactly when GC events occur and how much memory was freed. This information is invaluable for tuning your application to reduce pause times and improve overall responsiveness. Speaking of tuning, let's talk about optimization techniques to reduce CPU load without sacrificing performance. There are a lot of subtle ways to achieve this.
Absolutely. I've seen some improvements with minor tweaks.
One effective method is to minimize unnecessary computations. Lazy evaluation and memoization can save a lot of CPU cycles by avoiding redundant calculations.
Memoization definitely helps in recursive functions or repeated operations.
Exactly. Another technique is loop unrolling. By manually expanding loops, you can reduce the overhead of loop control instructions and potentially speed up execution.
Loop unrolling can be risky though, as it increases code size.
True, but it's a trade-off worth considering, especially in tight inner loops. Also, consider parallel processing. Using multiple cores effectively can distribute the workload and reduce overall CPU load per core.
Parallelism works well for data-intensive tasks.
Definitely. And don't overlook compiler optimizations. Modern compilers have advanced features like auto-vectorization that can significantly boost performance by utilizing SIMD instructions.
Compiler flags can make a big difference.
They sure can. Lastly, profiling tools can help identify bottlenecks that aren't immediately obvious. Once you find them, targeted optimizations can make a huge impact on reducing CPU load without compromising functionality.